Okay, so here's a very similar example for an athletics example where you want to say something about if someone tests positive for a performance-enhancing drug, what's the chance that they actually have that have been a drug cheat. So again, the prior is an issue here. So after winning a race, an Olympic runner is tested for the presence of steroids. It comes up positive. It's known, how do we know, but anyway, that 1% of all victorious Olympic runners do use performance-enhancing drugs, and for this particular test, the false positive is 95% and the probability of false positive is 2%. So again, now, what we do very simply, and I've got some slightly different slides that I'll talk you through in a minute, but the idea of a Bayes net is that you use a node in a network to represent the variable of interest. So the two variables, or the two things we're interested in here, the first of all is the hypothesis, which is the person a drug cheat, which is true or false. And then we've got another variable, which is do they get a positive test result or not, or the test result being positive or negative, if you like. So there's two variables, and I'm just going to draw here, which is one variable, which is drug cheat, and that's either true or false. And then I've got test result, and that can either be, these are both binary, positive or negative. Okay, you don't have to have them only having two possible values, but it keeps it simple for teaching purposes. Less alternatives to consider. The idea of the Bayes net is we've got our variables which have these particular values, and we don't know what they are, and we know that there's a sort of a relationship between whether you're a drug cheat and then what the test result will be. And in particular, we know, because of the way we represent it, that there is a conditional probability. There's the probability of the test result equaling positive, given that drug cheat is true. If you are a drug cheat, what's the chance you have a positive test result? We've got our information about this thing and the thing, and this is the 0.95. We've got, because there's only two alternatives, the test result equaling negative, given that you're a drug cheat, must be 0.05. That has to sum to 1, because they're the only alternatives. Remember, that whole probability mass must be 1. Then we've got if you're not a drug cheat equals false, what's the chance positive test result equal positive? So this is the false positive, because you're getting a positive test and it shouldn't be because you're not the cheat. Well, we've got 0.02, and of course then the chance of having a test result being negative, given that you're not a drug cheat, that's the rest of the probability mass, so it's 0.98. Okay, so this is our probabilities. Now in the Bayes net, the other thing is up here, we sort of have the probability of this in our problem as well. There's no arcs coming in. There's no other variables in our system. We could have it something like which country you're from, and it might depend on whether you're Russian or Chinese or from somewhere else. But at the moment, we just know that it's not conditioned on anything. So we've got our probability of drug cheat equaling true is 0.01 again, and equaling false is 0.99. Okay, so these are the numbers we've got from the problem. Now, I'm giving them to you. Later on, if you're starting with a new problem, you have to work out what are the key variables in your system, what are the probabilities associated with them given you don't know anything. If you work out there's a relationship between them and you know there's some conditional probability here, what they actually are. But I've given you them in the problem, but then we're showing how to put them into the model. So once we've got that, we've now got our nodes, which are defined with their states. We've worked out that this direction of this, and this is a kind of a causal direction, if you like. It's not that sometimes people actually put the arcs the other way. This is that if you're a drug cheat or not, that kind of leads to you getting the positive test result. If you want to think about it that way, you could draw it the other way, and you have to cast the conditional probabilities the other way. But this is the way we usually do this. Once we've got this, and this is what I would show you in Netica, and I'll run that later, is that you've got a model. At the start, this is our priors. You can actually, before you find out anything, you can work out what's the probability of getting that positive test result. How can you get a positive test result? You can get a positive test result if you were a drug cheat, and use this one. So that would be, you get a positive test result right here. What's the probability of the test result equaling positive? That's our two cases. It's that if you are a cheat, which is 0.01 times this probability, you'll get found, 0.95, or you are not a cheat and you get the false positive times 0.02. That's this probability. So you can work that out, and you can work out again the probability of it being negative, and it would be the opposite. So I don't know if anyone wants to do that in their head. I haven't got it written down because I was going to do it in Netica. So you've got, before you know anything, you've got numbers here and numbers here. Now, typically in this sort of model, I could say, all right, if someone definitely is, you can put in that number and it will change the numbers that come out on this one. Or I can say someone's come up positive, and you say, I know they got a positive result, and it will update the probability of these using Bayes' theorem, basically. There's an algorithm behind it that does kind of a whole lot of Bayes' computations. When there's only two nodes, it's pretty much doing exactly Bayes' updating. So you put these in with your nodes and your arcs and your conditional probabilities, and then anytime you like, you can say, yep, definitely, it's 100% that they got a positive test result, and these other numbers will move from 0.09 to, I think it actually moves up to 0.3. Was it 30?
It's about 1 in 3.
It's about 30.
Yeah,
It's about
0.0293.
02.
Unless I got it wrong.
I think you got it wrong. I think it's about 34%.
Yeah.
Yeah.
Oh, okay.
Yeah.
Copies.
Yeah. So you put this in there, and you don't have to sit there and do on hand or even in a calculator all your Bayes' theorem. So this is sort of what the Bayes net basically does. Is it takes a problem where you've got probabilities and relationships, in particular conditional probabilities, and can do these computations very fast and efficiently. Okay. Now what I'm going to do is I'm now going to take you through an example which I've given you the printout of.
We're allowed to look now?
Yes, you're allowed to look now. I'm just going to throw that water myself. Did anyone who want? So I've already shown you a picture of the Reverend Thomas Bayes. Now we've got Judea Pearl, who is a professor at UCLA, who in the 1980s in particular was one of the leading people in the AI and graphical modelling communities who developed Bayesian networks as a then new technology for reasoning under uncertainty. He also did a lot of work on sort of the nature of causality, and he, in I think 2012, was awarded the Turing Prize, which is like the Nobel Prize in computing. Okay, so I'm going to back a little bit. Bayes nets are graphs in mathematical sense, where there's a set of random variables which makes up the nodes in the network. They have a set of directed links or arrows or arcs. People use that terminology interchangeably to connect pairs of nodes. That each node has a conditional probability table associated with it that quantifies the effect in terms of the uncertainty that the parents have on that node. So when there's arrows coming in, you have a conditional probability table that says what's the probability of that node having certain values given its parent nodes, the arc node. And it's a directed acyclic graph, which means that you don't have any directed cycles. You can't start at one node and follow the arcs around and end up back to where you started from. That's not a valid Bayes net. So,
so you can always work out the probability of not probability, propagate things through. And
not have them count. Exactly. Because what actually happens is that there's various ways in which you can do that sort of updating, but if you think about it in terms of a message passing algorithm, you don't want to have things being passed on and then not coming back and counting as corroborating evidence when it started from the same place. So here's a toy example, but it does have elements of it that come up in real world problems related to environmental reasoning. So we've got a scenario where we have a river with tree-lined banks that's known to contain native fish populations which need to be conserved. So we're interested in an environmental issue here. Parts of the river pass through croplands and parts are susceptible to drought conditions. So, over longer term, we're talking about with drought. Pesticides are known to be used on the crops. Rainfall helps the native fish populations by maintaining the water flow in the river, which increases the habitat suitability they need as well as the connectivity between the different habitat areas, which also impacts on the health of the native populations. However, rain, which is needed to get the water into the river, which the fish need, can also wash pesticides that are dangerous to the fish from the croplands into the river. And there's a concern that the trees and the native fish will be affected by drought conditions and the crop pesticides. So this is a sort of a scenario. So at this point, the task is to sort of try and build a Bayes net to model the scenario that's described here. Often you'll have a more concrete one, which is to build a model so that we can say that for the next 3 or 4 years, for the different scenarios, what's the probability of the native fish sort of having a certain level of health, or are they going to be doing well or not well under different scenarios. We want to do some what-if scenarios to sort of work out what the risks to the fish are. It's usually better to have a more concrete target question, and that's what we'll be seeing in some of our for the Create project. They will be giving us these very specific questions that they want the analysis to answer. I didn't have time to modify this.
I was going to ask a question, but maybe it's part of the exercise.
Yes, this is the exercise. Okay, so the exercise is that we're going to go through building a Bayes net to capture that scenario. So the first step is, and the part of the first definition of the Bayesian network is that we say that if we've got these random variables that make up nodes in the network. So the step there is to say, well, what are the key things, variables in the system that we want to include in our model? What are the candidates for them?
So it could be something like,
Yeah, so it's basically a node represents a random variable which describes a system as being in several states with each state having a certain probability. We can have continuous variables. They can be discrete or continuous. We're going to talk about discrete where there's particular values rather than a real world quantity. I'm going to skip that now. This is just from my training slide. So what are the nodes to represent and what values can they take? So we've already seen before, I've talked about...
Can I interrupt for a second? You keep on clicking your pen.
Okay. Cut that one out.
Click.
Well, that's really bad because when I teach presentation skills, we video people and see if they have any sort of tics that are annoying, like swaying or pulling their ear or whatever. So clicking the pen was not a good one to have. Thank you, Paul. Okay, it can be Boolean, represent propositions, taking binary values true or false. So we could have a drought condition node representing the proposition that the region is suffering from a drought, something like that, okay?
Yep.
Or we could have, So I've got things ready to say what I think they should be, but now this is where I'm going to switch to the board and ask you what you think, and you may not agree with my take on it, and we'll probably go back to my version because I've got the rest of the example prepared. So what are the things, actually I'm just going to, they can be categorical, a node that represents a category or a group of things. So colour, red, yellow, blue. So that's not a quantity, that's just, a category that is not an obvious ordering unless you wanted to worry where they are on the rainbow spectrum.
I've missed the point of that.
Oh, it's just, you could have a node that represents the colour of something.
Oh, okay.
Yeah, so
right.
It's like any sort of variable.
Right, so these are examples of the discrete variables, basically. It could be...
Yeah, they can be ordered, they can be integral.
Okay, so you're just going through the things.
Yeah. Anyway, so So one way of looking at this is to say, well, what are the nouns in our description? Because they're concrete things that may have a state that we may be interested in. Okay. So here we've got river, banks. Oh, that pen's not very good, is it? Banks. Maybe fish populations.
And the banks matter because of our concern for the trees in native fish.
Yeah, maybe.
Right? Like
Yeah.
If not, probably not.
Yeah. We've got croplands, drought conditions, pesticides, rainfall, connectivity, to river connectivity, and water flow. Put them in the wrong order now. There's also a few other ones, habitat areas. I haven't even highlighted that, but it's not. Rain. I've already got rainfall. I could have rain as well. Is rainfall different from rain? Fish, river, croplands, and then we've got trees. And again, drought conditions and crop pesticides. So some of them are nearly synonyms or slightly different ways of saying the same thing. Okay. So we then have to look at these, and sometimes you realise that they're the same thing or they're less relevant and so on. At this point, in order to focus it in, we start saying, well, what's the key thing we're interested in? And I guess it's like the target variable, if you like. If we didn't have it in there, what would be the whole point of this system? And the key thing that we're interested about is the health of the native fish population. Okay, so that's where having a really well-phrased question that you're trying to answer helps. So at this point, the native fish population is going to be our starting point. Okay. Now, the question is, well, that's the variable thing we're interested in, and we're sort of interested in the health or the abundance of that. You haven't really said yet. And at this point, you have to get your experts to say at what level, what is the feature of it they'd be interested in. Sometimes they might think about a certain number of that fish in a certain area of the river at some density. And above a certain density is healthy, below a certain density it's under threat, and somewhere in the middle it's okay, not great. So one of the things that's really tricky here is that we can decide this is our variable, but especially if we want to have these discrete states, how do we define them in a way that's meaningful for that problem domain? So you have to have quite a bit of discussion about that, what you can observe, what makes sense to the experts, what are going to be the key things that will answer the question that we're interested in.
And that's probably highly relevant to us as well, because we're looking to produce written reports.
Yes, that's right.
Natural language.
Yeah. So I'm going to slightly sort of bias this, and I'm going to say that we've got our native fish population as it's actually one of the outcomes. We're interested in that being impacted on by all these other things, and it's in some sense it's not the kind of the driver of anything else. It's not like the native fish cause some other species to do well because they eat them and so on and so forth. This is kind of like the end point, the environmental end point, and that's how people in environmental management say that they're interested in. So one way to say from these candidate variables, if you like, what to do is to say, okay, we know we want to have something about this. We haven't said yet what its state should be and exactly what they might mean, but we know we have to have it in there. So we don't have to commit to those states yet. Let's just say that we have to have a variable in there that will represent that key thing.
The other thing, of course, is it's going to be dependent on its own initial value, right? Like there's going to be some initial fish population that is also an input variable to this, right?
Yes, so there is an issue with this problem about whether we're going to model as a time series or not. And for now, we're going to just kind of ignore that we might be talking about now and in 1 year and 5 years, and just say that given a certain configuration of longer term drought and rain this year and pesticides this year, what do we think is going to happen? So
there'll be an impact basically rather than a value.
Yeah, that's right. So we're talking about a time frame of sort of in a sort of a current year.
Sure.
And not trying to roll out over many years. We're going to do it as a sort of a one-off, and that's really important to identify as well. So, and again, to keep it simple, we could do this as a very complicated 20-year projection, but at this point, we're not going to. So given the way that the problem's been described, and these are our candidate things, these are all things that are relevant to the native fish, so they wouldn't have been in there. So you've got to be very careful about saying, well, what's going to impact directly on the fish population in the river? You can't just list all other 7 things that you've mentioned in the problem. They're going to be related somehow, but the question is, when we're interested in our Bayes net, we want to get the parent nodes of it first, which ones are directly influencing it. So going back to the way it's described in these things, what are the 2 or 3 key things that in a causal sense are making the fish population in particular do badly? Or if
Activity, water flow and pesticides, I guess.
okay, so we've got connectivity, water flow, and pesticides. Now,
Although maybe water flow is connectivity. Connectivity is
yeah, okay, so good point. So I'm going to skip forward a little bit, but what we actually would do in this, say, we could call this sort of the quality of the river in general and fold them in together, or we could have them being separate. Okay, so I think what I've actually done, as you'll see in a minute, I've got to pull this sort of river flow, and it's to do with that idea of the connectivity and the amount of water in it, and then we basically say it's kind of high, medium, or low, or good, average, poor, or something like that, to sort of summarise what might be individual factors, to keep it a bit more qualitative at this point. Okay, so we say that, yeah, if this is good, if there's got that right combination of features, then the fish will do well, and if we start having not enough water or not enough connectivity, they don't breed properly, they don't move around, they can't do what they need to do, and they'll start dropping off. Yep. What about pesticides? We think we've got in here that they'll be affected by drought conditions and crop pesticides.
I'm told they're bad.
Yeah, so pesticides are bad. Now, where did the pesticides go originally?
Only in the parts of the river that had the crops.
Okay,
Cropland.
but the
Only parts of the
original
river has cropland.
Yeah, the pesticides start on the croplands.
Yeah, and only parts of the river are affected by cropland.
Yeah, but if the farmer puts pesticides on and there's no rain to wash it into the river, what happens? It's no big deal for the fish. So pesticides in itself is not the direct thing. It's actually pesticides in the river.
Yeah. Sure.
Okay, some sort of concentration or whatever. Yeah. So it'll be these are the 2 factors. Do they have enough water? Can they move around the way they need to breed? And that's good and bad. And then even if this is good, if there's too much pesticide in the river, we sort of know from the problem description that that's going to be bad for them, probably kill them directly through some other causal mechanism. Okay? So we have to sort of choose these variables that are direct impacts, and then we take a step back and we actually say, right, well, we can pick either of these. On the river flow and connectivity, in general, if we look at what we've got, I didn't really define it, but imagine this is not this current year, but the previous 4 years or 5 years. Like the last 5 years or the last few years, have we been having drought? And drought is defined usually as a certain amount of rainfall below long-term averages, and they usually will have an impact where the ground itself becomes very dry. If you've been having long-term drought, there's just less moisture. Some of it's lower down and some of it's higher up and things. So the difference between that, and then there's the kind of the rainfall that will be in kind of the current season around growing the crops and the rain coming down and heading into the thing. Because the rainfall will be the thing that will flush the pesticide into the river, whereas the long-term drought will be something that is a part of the system, in particular, what the base level of the river flow is because of what seeps through from lower level water and so on. Okay, so picking that river flow then, this is like the pesticide bit of the system, and this is the water bit of the system. we've already kind of got a split already. So if we take this one and say, all right, what are of our variables? We've already kind of you put these ones in there. Let's say, well, what are the variables that we need to create and that will directly impact on the river flow? Yeah. So rainfall. Actually, put that across. Rainfall. And I'll put for you, and basically the drought. If one way to think about it is if it's been really dry for a long time, even if it rains, less of it will get into the river. Or it could be that it's so dry that you get a big downpour. In fact, none of it soaks in and it all comes in a big flood because it's all washing across the top. I mean, who knows what the actual dynamics will be, but there's some sort of interaction between how much is falling and how much ends up in the river, depending on what your physical model is of how it's getting there, whether it's coming off the top, whether it's seeking down and coming in and so on, whether you've got little creeks and things feeding in, who knows. Skipping all of that. Okay, that seems pretty straightforward. We don't know quite what that is yet. On this pesticide in the river, then this is where we go back and we have to say, well, what will determine how much ends in the river? Ends up in the river.
Rainfall, obviously.
Yeah, if there's no rainfall, it won't get washed in, and if there is, we've got a chance. And then
Croplands or
yeah, it's actually we go back and we've actually got the pesticide on the crops. So we've actually got, even though we didn't have two pesticides here, sort of we have to realise that there's two places in which there's pesticide and they're different variables in the system. So we can't always get it from the nouns directly. So we've got pesticide on crop. Okay. Now another aspect. Now I'm just going to put this in here because it makes it a little more interesting when we show the relationships. But it may well be that when we're going out and measuring things, what can we actually know? We can know whether we've had drought, we can observe rainfall, we can know what they do with this. We often don't know these things. We can go out and observe this. Another factor, though, is that we've got these trees on the banks of the river, and they may also kind of be an indicator. If all the trees are dying on the banks of the river because there's not enough water in it, or they've been long-term drought, then it's sort of it will tell us something about the health of the system overall, even though it's not causing the native fish to be dying directly. That's why we put it in there. So the idea is that if we put in tree condition here, it's sort of, if we find it out, it will tell us something about the other variables and be a back path, if you like, to giving us possibly changing our probabilities about some other things. So this one's a little bit up in the air. Like the tree condition, you can certainly imagine if we've had long-term drought that the trees might be struggling, because it's not just what's happening now. These big trees can be pretty resilient, but if there's been 5 years of drought and the water's been really low in that. So this is not the river flow now. It might be what's been happening over the last 5 years. So that suggests that long-term drought will be affecting the tree conditions. Now there's
I'm just wondering how you would make the decision as to whether or not you include something like that or no.
Yes. Sometimes if there's a piece of information that you know should be making a difference, you try and put it in there. And if it turns out later that you've got enough information of the rest and finding that out doesn't change anything, or you can decide to drop it off later. And it's really tricky at times. You could build this model without it, and then you can put it in. But it just it shows a sort of a slightly more complex model for teaching purposes than this, which is a little bit all straight down to here. Something sitting out here.
And when you're done, you can measure the sensitivity of some of these nodes. And
yes, exactly. And then you can go back and say, well, we shouldn't have even bothered, or yes, this is actually making a difference.
Right.
Especially, it depends. If you had really good access to weather data and you knew that, at this point, that's the only back path, and it's not going to help you. But if you don't have access to good estimates for what this was, this can tell you something. You know, no one's been keeping records here, but all I know is the trees look pretty bad. You know, So that might come up in other sorts of scenarios. It's a little bit artificial here. The other thing is, now, I think in this example that I'm going to carry forward, we did something like there's this year's rainfall. I've forgotten what I actually put in the model. You can imagine it's current year's rainfall and long-term one, something. Or you can imagine it's river flow, but remember the river flow was connectivity, and that probably doesn't matter to the trees. It's just have they got enough water in there, reaching their roots and so on. So I think we put it in like this, and it's a bit of a question, but that's right. Now, at this point, I had this all planned for a real-world training course. I was pretty pleased with myself. I got an environmental person to check it, and then I had someone say, "You've forgotten something in my training course." Another relationship that they wanted to put in there. Can anyone think of what that might be?
Based on the text, it would suggest that the pesticides might be an issue for the trees.
Exactly, yeah. So I said, what about the pesticide? Well, probably pesticide in the river going across to that, yes.
Well, and in fact, your problem originally said there's concern that the trees
Yes.
and native fish will be
Yeah,
affected.
exactly,
by that.
yeah.
That's something.
Yeah, so there's that. At this point, what I say is sometimes you make a choice and say that's true, but we want to keep it a bit simpler for our first iteration, so we're going to focus mostly on this. And when or someone could say, well, actually, this pesticide they use in this area doesn't really affect these trees. I don't even know what it might be. But anyway, at some point we kind of made a mistake and shouldn't have even put that in the description, and this is kind of one of those interesting things. So yes, we could have that in there, but I'm going to do the rest of the running example without it being there for now, and you can add it in later. So sometimes, especially if you think some of these connections are very weak, like it's not going to make much difference, the question is, do you put them all in? Because when you put them in, and we'll see in a minute, you have to make conditional probability tables, and every time you add a new parent, you basically double the size of the table. In fact, you double it if they're binary nodes for the parent, but depending on how many values that can take, you multiply by the number of possible states of that parent. So the tables get really big really soon. So you've got all these sort of choices. Now at this point we've done this, and this is where sometimes people say, Bayesian networks, quantitative methods, not very good. But I say at this point, we've talked about the system, got a picture in our head, you could call this a concept map or whatever, and this is skipping ahead a bit, but do we decide to show them this or show them a conceptual map that has nodes and arcs, and that this is sort of a negative relationship, and how do you annotate that? There's all sorts of choices around different ways that you draw this picture up, but at this point it's a qualitative model. There's no numbers there, we've just talked about it. The next thing you really need to do before we can put in the CPTs, though, is we do have to choose what the states are for these variables. And in our actual running example, we show a version where we have things like that says high and low, and below average, average, and above average. Things like that. At this point, keep them all 2 and 3. And then we change them into the ones that are actually possibly continuous variables. Something like the pesticide in the river might be some sort of actual concentration, and then you can discretize it, into below a certain concentration level and so on. And we actually have 4 versions of this network, all getting more complicated. Okay, so we've done a tech report showing how you do that, so I printed that off for you and show you later. So at this point, though, we have to make some choices about the values of the network. And if you were the real experts, and I hadn't made it up as a teaching example, it'd be up to you to work out what they were and what makes sense. Okay. And this is where there's a little bit of a problem, possibly with our BARD thing, is that I'm used to doing elicitation where there's people there who know the problem domain, whereas we've got a sort of a second stage where someone's collected all the information, the analysts have a certain amount of information about all sorts of things that they have to translate into a Bayes net, but they're not the domain experts themselves. There's like an extra stage.
So which begs the question, how well does the Bayesian nets in general deal with parts of the network having uncertainty? As in, like, let's say you have very complete information for 75% of it, but there's some portion of it that you haven't been provided the adequate information about to really.
Yeah. You can put in sort of arithmetic equations or like normal distributions showing relationships between things and things, so on. You don't have to like make up just a table of numbers. You can put in other arithmetic or statistical relationships between the variables, and we have to work out how to teach people about what's available and if there's a sort of if it's a noisy or some sort of relationship like that, we can capture those. Okay. So I'm coming ahead a little bit for people who don't know anything about Bayes nets.
Right, but if your question was uncertainty based on the limited information that you have and the judgments that you've made, in a certain way, the answer is that they can handle that very well.
Because you're just doing low probabilities rather than...
What you can do is there's built-in functions to assess the sensitivity right, of the result. So you're interested in the fish population.
Yep.
And so you assess the sensitivity of that to the different probabilities that you might have put in for some of the other variables.
So you basically run the system with whole ranges of possible values and see the effect and then make decisions on which parts. Okay.
That's right.
Yeah.
So, I mean, that's not a complete answer because I'm assuming that the uncertainty is kind of limited to a location where you can run a sensitivity, and the uncertainty might be a bit more pervasive than that. It might affect the structure, it might affect all sorts of things. But that is something that we can deal with potentially very well, as long as that information is in there and we run the right diagnostics.
There is also, there's a whole separate discussion about this, but when we get to sort of have a input into the problems they're going to use for evaluating, and there is a question about whether the information that's provided to the analyst is in itself enough for them to come up with kind of the right answer or a range of the right answers. And the idea is that, even in this sort of problem, that they'd be given enough hints about what certain probabilities are and what this relationship is and so on, that they can then translate it into the Bayes net. That then apparently they're not supposed to go off and be searching Wikipedia for huge amounts of information that's not provided as part of the scenario. So that's something that hasn't been decided yet, but I think that we can handle it when there's a few missing bits because we guide them how to come up with some sensible estimates, or at least run the thing under 3 or 4 different scenarios, whereas some other methods might not have a way of doing it. But we're not imagining that. See, I do this for people who want to build a Bayes net for their problem where no one's even found all the pieces yet. That while they're doing this modelling, they realise they need to go off and find out how accurate the test is and how sensitive these trees are to drought, given what species they are, and all sorts of things. So it becomes you can never usually do it in a 2-hour session because you identify the key portions and then someone has to go up and find things in the literature or observations or run data collection on how to actually build the rest of the model. So that's a difference between the way we do it with our expert elicitation compared with this sort of...
So in part that's just going to be a difference between Phase 1, Phase 2 and Phase 3 of this project, assuming that we get all the way through.
Yeah.
So in Phase 3, there'll definitely be research allowed. So we are looking forward to that because, as Anne said, building a model can show you what you don't know, and it can show you what you maybe need more research from. And so we're looking forward because that will be good for us. Phase 1, by contrast, is they're going to be very self-contained little problems, actually most of them fairly small. So in that sense, it's like a little puzzle where all the information's been provided. And so if you imagine that this sheet contained all the information to compute the answer. So this is one of the problems, is that they want a correct answer. They want all the information to be included in the problem, and they want the problem to be concisely stated. So that really constrains the kind of problems that they're going to be able to give us in Phase 1. Concise, contains all information, there is a right answer. So if that were the case for a real problem of uncertainty like this, then effectively they would be giving you the statistics like we saw for the test, the
cancer test
or the steroid test. Yeah. So where we actually had the numbers. Yeah. So in that case, it's unambiguously a correct answer to that question. And even if something that I pushed for or tried to bring to their attention is that which was a property of the example we gave them on prostate cancer, was that you might have all numbers but one, for example. right? And there's still a correct answer. It's just relative to what that last one number was. So you do that sensitivity on that last number.
Yeah.
So you say, if it was this, the answer's that. If it was this, the answer's that. Now that's a correct answer. It's a little bit more complicated because it has that one uncertainty.
Okay. Now, I have got some slides here which I'm going to also print out for you so you can have a look, or we might do a video of them separately. But, it was talking through endpoints, and then this is, when you're doing it with domain experts, you've actually got to put it in the terminology they're used to. They're used to the endpoints, the water-related stresses, and the pesticide stressor. That this is the way in which they think about the parts of the system. So we actually didn't put in the crops, and later on in one of the more complicated models, there's always going to be a trade-off. At this point, if you don't put the crops in, you always say don't put the pesticides on the crops because that'll be better for the fish. It's actually going to be a trade-off between how well the crops do, how much money the farmer makes, and so on. Yeah. So this is only half the problem, but it's a starting one, and we'll show that in the examples. So here's how you would go through, and for each of the nodes you make a decision on what they might be. And if you have a look here, you could have just a binary good poor for the trees, or you could have an ordered one where there's three values where there's actually an implied order even though they're not numerical, going from good to bad. I think we actually choose this one. The native fish ordered high, medium and low, river flow, high, medium and low, drought binary, just yes, no, this is more like drought over the last 5 years. Pesticide use, again, just high and low is too simplistic, but it keeps the table small. And then rainfall, you could have these discretized values, or you can label them with these numbers. So that's really, you don't have to commit to these, but you have to put them in at some stage. You can change them later, but before you can do your conditional probability table stuff, you have to move on with that. So we've talked about these directed links and arcs, and it really makes sense to talk about both the variables and the arcs in an interspersed way. I mean, we can come up with all these and think about what they are, but if you think about them too much, you might be worrying about the values of ones that don't even end up in here once you work out which are the main things. So that's why it's very tricky to know the right way to interleave that. Just a little bit of terminology. We try to build causal Bayes nets, but sometimes you put things in that possibly are not a direct cause, but there's other variables in the system that you might not be modelling. You're kind of leaving out a whole chain of causal things, so there's nothing else you want to put in there. So we say direct influence or something, but it's a little bit tricky.
Is that just saying you might have a single path of things and you just collapse them down
to one? Because you don't know enough about all the intermediate conditional probabilities. You can never know them. Sure. So it just this is what I did. I started off and said, well, what influences that native fish abundance, population abundance, and then they're the ones that go into it, the arcs going into it. What influences the river flow? What influences the pesticide in the river? What influences trees? So that's what I did on the whiteboard. Yeah. And then, so this is the one that we actually want to run. And then there's talking about what's been left out and documenting. It's really important. So, Eric, for the augmented one, what's not there, and in particular what arcs aren't there, is really interesting because that's not even attached to a node or an arc that's there. There's this for the network, what's been left out would be quite interesting. We've decided not to put in the crops, and we've left off the arc from the pesticide in the river to the trees. Yeah. So this is something that these are my prepared slides. We do this all the time, and sometimes we do it consciously to keep the problem down smaller, see if we still get a reasonable answer, get something, and then realise, well, it's still not giving us enough, we have to add a bit more.
So that's interesting. I'm just listening to talking about your experiences of elicitation. How easy is it to evaluate whether the Bayesian network you've produced is good or is working? Because obviously you've got some knowledge of how you expect it to.
So once you build it as a whole, and you've put in values in the CPT, and if I was showing you on Netica, then I can show you. You can do what-if scenarios are very helpful, and experts like that. I think I've got them either here or I'll bring them up in a minute. That I'll just catch up. We talk about parents to children with this arc, and ancestors to descendants, as sort of a family tree model. For computer scientists, we have an upside down tree where we have root nodes at the top with no parents, leaf nodes at the bottom and intermediate in the middle. Now, whether we choose to use any of
Oh,
those...
way round, right? Leaf nodes,
Leaf-
not with a root.
No, these are the leaves.
Oh,
The trees, well, I've laid them out like this, but this is...
okay, sure, all right.
But it is
But I
an
mean, there's
outside...
multiple, roots and multiple leaves.
Yeah. So
Okay.
I'm just saying how we do it. Root nodes,
Sure.
leaf nodes, and
It
intermediate.
makes sense they're root because they're...
So here's a picture.
origins.
Root nodes, intermediate, and leaf
Okay.
nodes. So the leaves are the fish abundance. With no children, you're a leaf node in BaseNet. I don't know whether any of this we need to use when we're building our system or not, but I'm just saying how we do it in a technical sense. Now, layout conventions, these are mine. Root nodes at the top, leaves at the bottom, and arcs kind of going down the page or even with time across the page. Many people, especially once they're trying to fit, say, 20 nodes on one page, end up moving them all around just to squash them onto the page, and it's terrible. It's like spaghetti. So, but even something like this, there's no narrative or story around this. It's the same network. Okay, so there's a lot of, I mean, if you went consistently up, it'd be one thing, but kind of tree condition here. So this is a background factor. This is a root node, and that's a leaf node sitting next to each other. I mean, once you lay it out like this, no one has any intuition about it. Now, sometimes when you do it on the whiteboard or in Netica, you get a mess, and you've got to take a step back and say, let's do it again. Like, take the mess and relay it out in a sensible way. And some people, they actually, especially once they're in the software, they start moving things around to fit as much on the page as possible, and they end up giving they all fit there, but no one looking at it has any, even the person who built it really from that picture would understand the causal narrative around it.
And there are layout algorithms that do this.
Yes, and Michael and
There's lots,
these guys are like graph layout
we
experts.
do lots of graph layouts.
Yeah, but I'm just telling you what the norm
We can
is.
leverage all of that sort of stuff.
Yeah.
We should, because you're right.
Yeah.
So causal ordering is a big feature here, like that we want.
But you want to emphasise the important pathways.
Yeah. So if all the arrows are, if you don't have arrows going in the opposite direction.
Yeah. And you try and minimise the overlap.
Directed graph layouts.
Yeah, and when they're really complicated, some people just let them go through because the software lets you, but if an arc goes underneath here, you sort of lose the picture of it. It looks like it's going through there and it's not. So then you try and do them like this. And
occlusion is bad.
Yeah. So that will be a factor for the layout people. So we're going to talk about the conditional probability tables. So here we've got a little fragment, our little bit at the bottom where we've got two parents. And we've got the problem of the fish. I'm not sure why we put a double bar in here, by the way. It should be given the two parents. So these are given, these are the variables at this stage. So that's a whole distribution at this point because it's given all the possible values of all of them when you write it like this. So next thing we do is, and I'm not going to elicit this because you wouldn't do an elicitation like this in a normal sort of setting, or you might, but anyway. Basically, I'm going to show when I'm explaining what CPTs are. I'm not going to show you how I get them because I wouldn't do it like here, stand up here and put them in these boxes.
Yeah.
And I haven't got. I don't run this example to do elicitation of a probability. We have a session later on in our training course on that. So at this point, I've got them there and I just show what they look like. So in Netica, they have the parent nodes here as a column each on the left. And then they go through and you have for the two values of high and low, and then the two values of high and low with that. So you've got your 4 rows in your table, all the possibilities. Now, in Netica, you can actually drop and drag and change the order around, which is really good. So it actually flips them around. And it's easy to compare things when they're next to each other. In the table, it's really hard to compare something that starts moving further away. And by changing the order of these, you can get different things next to each other. It's hard. I would show you if I had Netica running. Yeah. So at this point, we've only got 4 combinations, which is why I kept them nice and binary, but even though it's unrealistic. And we've got our fish abundance, and I've given that 3 values. This is just so that, because I learned when I was teaching AI undergraduate, if you only ever use binary ones, people, when they do their first problem, make everything binary if they've never seen a non-binary variable, and they often get them wrong because some things are more than 2 values. So I put this in the first example they see, so they see at least something that's got 3 values. So our fish abundance is high, medium, or low. We've just got high and low and good and poor for river flow.
Sorry, and just to be clear, I know you wanted to skip the elicitation
That's right.
stage,
Yeah.
but these are numbers
That you have to get from somewhere.
derived from asking people.
Yes.
And literally case by case, you might say, if the pesticide was high and
Yes.
river was poor, what would you
Yes.
say the native fish impact is?
Yes, and Stephen's got some things where we have a little slider bar with colours over the three values where you can kind of move them, because each row has to sum to 1. So that's one way of doing it with slider bars. Another way is to ask the questions one at a time. In fact, you ask 2 of them, and the last one is supposed to be the one minus the other ones. So especially if they're binary, only ask the true case or one case. Sometimes you can also ask them and they give an answer like really high or equal or unlikely or whatever, and then you map them into probabilities. And we've got whole bodies of work on not actually asking the numbers at all. So there's a whole lot of work
to
on
the point that there's something there you would look at using already that you trust, or you still think that's kind of an open problem?
We've had little prototype little pieces of things that we might be able to use if we decide that giving them big tables of numbers, which anything more than about 8 rows becomes problematic. Okay, so here the key thing to realise is that of these 4 cases, pesticide in the river being high and river flow being poor, this row here is the one that's worse for the fish. Now, this visualisation doesn't show that. You know, you can go and look and you see, low abundance, which is bad for the fish, is really high, 89% here, and the chance of them having high abundance is 1 in 100, really low. So this one is the worst case for the fish. And the best case for the fish is where there's the highest high abundance, which is here, and that's where there's low pesticide and good. Well, this is what we'd expect. I mean, it's not an accident. We've made this the worst, this the best, and these ones are somewhere in the middle. Now, the numbers about the somewhere in the middle, no matter how we got them, actually give us sort of a ranking on it. If you can see here that when the river flow is poor, it's still really low chance. Like the fish don't do well if the water isn't right, okay? Whereas if the river flow is good, even with high pesticide in the river, this is higher. So there's a kind of like the river flow is going to have, we've made it be more important than the pesticide by these numbers, or it's reflecting that's what some expert judgment or what the stats said or whatever. So you can't really see that in this table unless you go in and look at it. So it's not a good visualization. And then when you look at the Bayesian Net software, when you're looking at the nodes and arcs, you only see these tables by bringing up a separate window. And it's not easy to see what these influences are.
And in terms of elicitation, now I'm doing something Shane was saying, asking about elicitation. But does that mean you're also having to generate these tables, maybe not in numeric form, but in the form of these categories, high, good, poor, for each of the intermediate nodes, everything that's not a root, right?
Yes.
So potentially a lot of questions you ask people about.
So when we did our tool, which we're going to demo next, like we're going to set up get everyone collaboratively to use the tool we did. We actually only picked some of the nodes to even ask them on. No, we asked them on all, but we didn't pick all the rows to ask them about, because you can do a kind of, if you know that things are going from bad to good and so on, you can kind of pick the worst cases and a couple of the middle ones and then kind of interpolate between them.
Yep.
And we have got little formulas to do that, and that's what we did for that example.
Right.
So there's one of these tables for every node in the network. Each row must sum to 1, so that's why we can use slider bars and all sorts of things. And the more, if you've got n parents, Boolean being true, false, then you've got 2 to the n plus 1 probabilities. So every time you go from A to AB, to, it's doubling in size.
Yeah.
So we do want to have a kind of a pressure during the elicitation for don't add things unless they're the main factors. It's really hard to know what that is, or put the main factors in, note that you haven't put one of these weak factors in, and then do it later if you've got time, because it really slows down the elicitation process, unless you've got a nice formula for, or some logical relationship for generating, in which case it's okay. But if you have to do anything like elicitation or estimates or judgment calls, every time you add another parent in, it really means a lot more cognitive load and time to get those parameters in there.
So I guess if you could ask questions that tell you about the behaviour of something, so even if it had 5 possible ranges, you know that the behaviour of it is it goes from good to bad in a sort of linear way, then sure, like you can just ask about the extremes and, as you say, interpolate between.
Yeah.
But if you had something that acts as like some probability distribution where the middle band it produces a bad result and the outside doesn't. It's more about asking that question and then the behaviour, right?
Yeah. If there's kind of an additive function of goodness and badness, in fact, we've got ways in which you ask about the impact of individual factors and then you kind of combine them. So the more of the good factors you've got and the more of the bad factors you can keep them. It's really nice. You add a bit of uncertainty around it and it works quite well. It's when you've got these synergistic and exceptions and there's the idea that some variables in some states become enablers of something happening and if they're not there, then the whole system behaves differently and so on, that they're really tricky. You can... We've got terminology around that. If you look at that knowledge engineering chapter in Kevin and my book, which I'll show you later, talk about the English words and the ideas of those sorts of relationships that you end up trying to capture. And you can think about them here before you worry about the numbers and then work out what sort of elicitation to do. So often when I'm doing this, I write down little words about the nature of the relationship. This is a positive thing, or that this is an enabler, or this is a moderating factor. This is, treatment or an intervention. You can put down little labels on what people are thinking of about what those relationships are. Okay, so I wanted to point out a modelling error, if you like, around this. Probabilities for the so this is for the one at the top. You have to get these non-conditioned ones, which are your priors. So this rainfall being below average, average, and above average, like this. And then in Netica it appears as a row. Modelling error, kind of a modelling error. The way I've named these variables and the nature of this distribution is a bit odd. I've got twice the probability mass for above average as below average. So it's not clear that this is really average. Now, I should have called it normal or the medium range, especially if it's between like 50 and 200 millimetres and there's below 50 millimetres, and people think that those values are the important ones for the river flow, but calling it below average, average and above average can be a bit problematic if it's not a symmetric distribution. Okay, so I left that in there at some point so I could point that out rather than just fixing it up. Because that's what you happen. You make these decisions and then you work through it a bit further and you realise that, I shouldn't have called it this, I should have called it something else. Okay, so there's that. And what are the other C's? And then the software. Okay, so what I would do at this point, and I'm going to see if I can get it running. I'm really tempted to download Netica, but whatever. I would show you that native fish in there and I would walk you through some what-if scenarios so you could see how you can set drought nodes and rainfall and pesticide in different combinations and you can see the effect on the fish. And then I'd say, well, let's observe that the native fish are doing badly. So you set that value to being poor and you see what happens to it means it was more likely that you're suffering from drought or that there was high pesticide use or something. It changes it both ways, if you observe that the fish are doing well or badly and then you're diagnosing what caused it. Or you say, what if, here's my scenario, what do I think is going to happen to the fish in the trees? And that's really the way you would use it, and you then get you an understanding of, is it behaving the way you expect? So what I might do is I might do a little video of myself, of a screen where I walk someone through, like Netica, and just click on things and do a voiceover, in the way that I just show how the network's working and how there's certain numbers and so on. I think I can do that. If I can work out a screen capture, I think that's easy enough. I'm really mindful.
You can use QuickTime on the Mac.
Okay.
You can just do QuickTime.
I did a little. I didn't have my. I just got my Mac last year when I did the training course on that. So.
Yeah.
All right. We were delayed starting and we had some interesting little side discussions along the way, apart from the technical glitches. So I think I'll finish up the videoing now. I think I'll.